Hello, Internet. Let me start by showing you the end. We have here on the left-hand side an image of your retina, and as you can see, they're hardly visible with the naked eye. In this picture, in this image, is if you're looking for a diabetic retinopathy, some lesions, 1, 2, 3, 4, hardly visible with the naked eye. And what I want is a computer system, an explainable AI system that has been trained on this particular diabetic retinopathy, let's call it condition, so that it helps me and augments potential areas of regions of interest here in this pixel, in this image, where it indicates which pixel the trained AI model thinks, a deep neural network model thinks it has discovered some regions of interest for this specific diabetic retinopathy. And this is exactly what we're going to do. We're going to have a look at the code on TensorFlow, Python TensorFlow, to indicate if you have a particular image and you have a model that is trained for analyzing this image for a specific purpose, how to do this. So let's start from the beginning. There was, of course, in June 2017, a beautiful preprint called Axiomatic Attribution for Deep Networks. And here they said they studied the problem of attributing the prediction of a deep neural network to its input features. So how, if you change the input features, would the prediction of the network change, in what quantity, and what are the most significant input features we're looking for? So what are, if you want in another way, the regions we're looking for in a particular image that would indicate to us where the network has been trained, hey, be careful, those are the regions of interest that I identified in this original image, which would indicate with a certain probability that we have here maybe diabetic retinopathy. This is it. What was the problem, what they set out to do? And if you want to do it yourself, we have here a COLAB notebook, a Jupyter notebook, and we start where we always start. We have some TensorFlow Hub, we have our NumPy, and of course our beloved Matplotlib library. So what we do is we download a pre-trained image classifier from the TensorFlow Hub. You don't have to care at all about what it is, why it is. As you can see, we have here a methodology where we have 224 pixels, and this is it. The expected input shape for this model is 224, 2243. Suppose this is RGB, RGB color pixels normalized to range 0, 1. And the output is, of course, a tensor of logits. Okay, so what we do, we say yes, okay. This is not of importance for us, so we just let the thing do its work. And then we just load some images. And we have one image of a fireboat and one image of a giant panda. So what we do, we load these images, we have a look at them. Yes, there's a fireboat and there's a beautiful panda. And then we say, okay, we have downloaded a system for classification of images. So we now apply this model on our two little images. And the first is the fireboat. And the fireboat tells us, hey, with a probability of 33% almost, this is a fireboat. With a probability of 13%, it's a pier or a suspension bridge with 5%. And with the giant panda, oh, much better, we have here probability of almost 90%. So this is it, this is great. But now I want to show you that the methodology that was identified here in this beautiful paper of 2017. And they found a methodology, and they called this integrated gradients. So we have a gradient here, and then we have an integral over the gradients. And the nice thing is that they say our method requires no modification to the original neural network, and is extremely simple to implement. This is why we are going with this model. If I want to show you the code, and this code, this notebook, you can download in COLAB from Google itself. I give you the link in the description to this video, so I would suppose download this notebook, start it up, and maybe you go along with me when we do the calculations for our integrated gradients. So yes, I do not want to go about the ImageNet classification. I hope you are familiar with this. This is not what we are looking for, but what we are looking for here is a path integral. And you know path integral, you love them as I love path integral, quantum field theory, Feynman, yes, most famous integral. But if you have here a look at the pixels, and remember, we want to have a slightly moderation, an alteration to the input feature, to our input data, and then we want to check if the prediction of the model, in our case it's an image classification model, changes. And if you plot here, if you have a pixel value, how does it change the gradient of the pixel? You see that at a certain threshold, and as let's say here this is 0.8, the gradient is not greater 0, but becomes almost equal 0. Yeah, doesn't make sense. And then the intuition behind the integrated gradient model or the methodology is to accumulate the pixel local gradients and attribute its importance as a score. So what you do, you have here your baseline, and your baseline, it depends, it can be a black picture or a white picture or a white noise or whatever you choose as your specific baseline. It depends on the data you want to analyze. And then you have your input picture, and this is our original picture of the fireboat. And then you have steps in between where you pause, you make your calculations, you go on, you pause, you make your calculations. And as you can see, this is a linear path. And this is from this model, we have a linear path. And we want to calculate the gradient. So what is now easy? You can break down to compute integrated gradients in 3 parts. Now let's follow the theory. You interpolate small steps along a straight line in the feature space. Here our, let's call it orange line between 0. This is our baseline, our black picture or our reference picture, and the input pixel value of our original picture of the fireboat. And then we simply compute the gradients at each step between your model's prediction with respect to each step. So we will have pictures here from black to the intensity 100% of our original photo, of our original picture, and we calculate at each step the gradients. And then we approximate the integral, because integral is quite intensive, between our baseline and input by accumulating a now cumulative average of those local gradients. And if you want, this is a little bit tricky. You can use different methodologies, Riemann methodologies, but this is not important for us. What we're looking for, now the first, we have to create our baseline, and then we have to grade the pictures, the photos on each step of this orange path. So let's do this. Now the baseline is very simple. We have TensorFlow zeros. We have a picture of the shape 2024 pixels times 2024 pixels. And let's run with this. And here's our baseline image. Exactly the same form, shape of the tensor as our original image. And of course, yes, you're not going to do this for your real application with just 200 pixels times 200 pixels. I don't know, you take 4,000 pixels times 4,000 or whatever you have the computational resources for. But this is just a demonstration. So we go with 224 times 224 and RGB 3. Then the formula. Now this is the famous formula for calculating the integrated gradients. And this is our integral here. As you can see here, we integrate over alpha. Alpha is an interpolation constant to perturb the features by, and we integrate from alpha equals 0, as I showed you the origin of the path, to 1 to our original image. Now they say computing integral is not always numerical possible and can be computationally costly, so we do an approximation. Well, of course. And as you can see here, our beautiful integral here suddenly moves to a discrete sum. Some normalization is taking place. It's not important how this formula merges to this formula, but let's do it. Let's do this integration. So as I told you, we have to have steps on our orange line. And here we say we have 50 steps. And we have to have m steps plus 1 because 51 would be our original image, our full intensity image. So we define this, and then we define interpolated images. So let's do this. You don't have to care about how it is done. Just look at the result. So here we have our alpha 0. This is our baseline. This is black. And then at the other end of the spectrum, we have alpha maximum. This is 1.0. This is full intensity of our pixels. And in between, we have certain steps at certain alpha, 0.2, 0.4, 0.6, 0.8. Whatever you change, you can define here the interval for this. So then you have now those pictures. And we have a model for image classification, and we know that the fireboard boat has what it is, 555. Yeah, I think 555 is the code for the fireboard. And then we compute now the gradients. And this is the fine, beautiful part that is happening in this model. So to calculate the gradients in order to measure the relationship between changes to a feature in our input space and the changes in the model's prediction. And the model prediction, the output space, is simply, this is a fireboat, code 555, or this is a pier, I don't know, 525 or whatever. So if we change the input feature, how does it change the model prediction? And what we do, we have now a function here, compute the gradient of a set of images and with a target class ID. And our target class ID is, we know it's a fireboat. And we have, let's say, 5 or 6 images. So you define this function, and then you compute the gradients for each image along the interpolation path with respect to the correct output. And we know it's a fireboat. So you go dot, and then you have here compute gradients. Now we activate our function. Our images are the interpolated images. These are those images here. And the target class is 555 is fireboat. So we do this. Gives us the gradient for every pixel of every image along the interpolation path. And this is exactly what we're looking for. The gradient for every pixel of every image along our orange path, and we know exactly what is our target class ID, and we think of these gradients as measuring the change in our model prediction for each small step in the feature space in our input space. And of course, if you want to have a look at the shape of the tensors, it is 224, 224. Well, of course. So we can now visualize the gradient saturation. This is an interesting part of it. Have a look at it. And as you can see here, this is our alpha, this is our black picture, and this is our full intensity photo. And you can see here the target class prediction probability over alpha, that at around, I don't know, 0.6 alpha, we have 40% plateauing our model. So at 0.6 alpha, we have a 30% maximum model target class probability. Beautiful. And of course, if you look at the average pixel gradient normalized over alpha here on the right side, you see that even before we have our plateauing at 0.6 here, there is the maximum information here before our plateauing. So of course the system learns before it reaches the plateau, because after the plateau there's nothing more to learn. So it is learning before it reaches the plateau area, if you want. And so to be absolutely correct, we follow here the text. Your model learns the most. The model learns the most from gradients at lower values of alpha before saturating. So saturation is taking place at 0.6. And as you can see, the model learns here, peak 1, here it learns before it reaches saturation. You can think of this as your model has learned the pixel. In our example, is the water cannons of the fireboat. To make the correct prediction, this is a fireboat because I can identify the water cannons. Setting the pixel gradients to 0, but is still quite uncertain and focused on other bridge or water jet pixels as the alpha value approaches the original input image. So here at 1. So this here is a little bit of pixel of water, dust or whatsoever. So to make sure these important water cannon pixels, which are the main object of identifying our visual recognition deep neural network, and we have the prediction fireboat, to learn how to accumulate these gradients. Okay, integral approximation. This is Riemann trapezoidal. This is boring mathematical stuff. You can read it, you can learn it, you can experiment with it, but we're doing the integral. Full stop. This is it. Congratulations! And now we're putting it all together. Now we define our integrated gradients function, if you want. And this is our formula, and this is beautifully 5 steps, and this is a very nice presentation here by TensorFlow. This is original TensorFlow notebook from Google, and it's available here on COLAB, and the link is in the description of this video, so download it and play around with it yourself. So first step is we generate our alphas, and our alphas here is KOM. Then we generate our interpolated images. Then we compute the gradients between the model output prediction with respect to the input features. And here you can see we have the derivation of a specific interpolated path input function according to the pixel differentiation. Then we have integral approximations through averaging our gradients. And then we normalize our gradients to the original image. Okay, so this is it. And here, this is it. This is the formula we are looking for. And you can see these are 30 lines of code. And this is exactly what we are looking for. We want to identify the pixel in a photo, in a picture, that allows the trained deep neural network to do an image classification. We want to highlight this pixel. If we have the retina pixel, we want to see where are the lesions in these retina pixels so that the system comes up with a medical diagnosis. Okay, again, generate the alpha. So it's again those 5 steps. I mean, I don't have to... Where are my 5 steps? Here are my 5 steps. Now this is the code of the 5 steps. Generate my alpha. Collect the gradients. Of course, maybe it doesn't fit in memory. Batch size. Gradient batch, yes. Stack the batch together for a single tensor. Of course, we are TensorFlow. Integral approximation. This is the trick with our Riemann trapezoidal. And then we scale the integrated gradients with respect to the input. And this is it. This is it. If we have this function defined, and you can define this for all your function, independently if you have a vision-based model or a textual model or a tabular data, you can use this beautifully everywhere. This is so beautiful. Then we have the batch function, and then here we go. Integrated gradients, now we apply it. And we say our baseline is our baseline. This is the black picture. Our image tensors are the fireboat. Our target class is 555, the fireboat, and the number of steps are 240. So it takes 12 seconds to calculate this on the COLAB with a GPU enabled. And the resulting tensor, of course, is an exact range that we have our original picture. And the nice thing now is we want to visualize the attribution. Now we want to have an explainable AI system where we tell the system, and this is easy if you have a vision, if you have a picture in front of you and you say, hey, which pixel of this particular picture led you to your prediction that this is a Firebird? And this is what we're going to do next. We're going to say, yeah, okay, do it, look at it, and then plot it. And if everything goes right, yes, here we are. Here we are. So this is our baseline image. Of course, it is black. This is our original image. Yeah, this is the Firebird with a resolution of 224 times 224 or whatever. And here is what we are looking for, the attribution mask. These are all the different pixels. You can have here color-coded legend maybe, where the picture says, hey, those are the pixels, the configurations of the pixels that lead to my prediction, and I am an image classifier model. And then you have an overlay over your picture, and you can see, yeah, this is really it. I mean, we are here in a very low resolution picture. If you do some high resolution calculation, it takes, of course, more resources, more time. But I think it would be better to show you that really the water cannons here, this water, these fountains of water here are really then those pixels that identify for our deep neural network that this is a Firebird. And as you can see here in the attribution mask, the boat itself is black. You see this here? This little red boat? It is black, so it is not the boat. Oh, maybe it's a ship, sorry. I'm not no sail at all. That does not contribute at all. It is the specific characteristic of the water fountains that say this is a boat, which is interesting. Because imagine those water fountains would have been produced by something else, like a ponton, not a boat, but another topic. And as you can see, the bridge here, the black pictures, the black pixels here, they are not at all contributing to the attribution mask. So you can clearly see here, those are the pixels where the system says, hey, because of those pixels, I have been trained, all my layers and my weights have been trained to identify if I see this pixel configuration, I say there's a very high probability this is a Firebird. So very easy code from 2017, a beautiful methodology, independent. If you have picture, if you have text or tabular input data, you can apply this. You do not have to alter your original neural model. Limitations, yeah. Okay, there's another example of a panda. The target class IDX of panda is 389. If you're not familiar with it, I had no idea. The steps is now 55. The tensor triggered, yeah, okay. Attribution mask. And so again, this is our baseline image, it's black. Now, black and white, this is nice, but be careful. If you have a really black object, you cannot use a black baseline image, but of course. So this is the original image, this is the attribution mask, and the model says, hey, I've been trained. If I find this configuration of pixels, and this is here the overlay where I say here around the nose and over there and over there. So not at all the little nose here, the smile, or the ears. I thought that ears maybe have a strong contribution, a strong feature attribution for the identification of the classification. But no, the ears do not participate at all at this particular trained model. Use and limitations. And I think this is interesting that they provide us with this additional information. Do the features highlighted by this technique match your intuition? And this is always good if you check the human factor, the human-machine interface, if you want. And if you get a result that does not match at all what you expected, or if the pixels are somewhere here and not at all characteristic for the shape or form of the body you want to identify, then you know that your model may not go forward. You have to do some debugging to do. Limitations. Integrated gradients provide feature importance on individual examples. However, it does not provide global feature importance across an entire dataset. Of course, it is a single picture. Integrated gradients provide individual feature importances. But it does not explain feature interaction and combinations. Of course, I think you would have to have some logical algebraic function for this. And then if you want to go on, you can find an even lengthier version of this tutorial here in this notebook. You will have the link in the description of this video. And again, if you want to have a look at the original preprint, you find it here in Archive from June 2017. And it is exactly this publication where I showed you here this example, and this is the point where we started with our video. This is it for today. I hope you enjoyed it a little bit. It is a complete example. You can play around with it, do some steps, I don't know, just do 5 steps and increase an overlay for whatever. Get a feeling if you play around with this model. This is the beautiful part. If you have an operational Jupyter notebook, you really can, you take your pictures, try to define a model, insert your pictures, and you will be amazed what the model identifies as the most important significant pixels in your picture to make a classification. This was it for this video, and I hope I see you in the next one.